Earthquakes occur because massive tectonic plates beneath the Earth are constantly shifting.
When that stress becomes too great, the crust suddenly snaps, releasing powerful seismic energy. Convergent boundaries create the strongest quakes, while transform boundaries can trigger sudden, violent jolts. Understanding this hidden movement helps scientists assess danger zones, though prediction remains impossible.
Deep underground, rocks along a fault line behave like a stretched rubber band. For years, they bend and deform as us.
This stored energy doesn't vanish, it waits. When the fault can no longer hold the stress, this release is called the elastic rebound. The rocks snap back into place, sending seismic waves out. These waves race through the Earth, shaking buildings, landscapes, and everything in their path. Elastic rebound is the core mechanism behind most earthquakes and explains how immense geological stress. At divergent boundaries, tectonic plates slowly pull away from each other, creating cracks deep beneath the ocean. Though they're usually less destructive, they occur frequently and help shape the ocean floor.
Divergent boundaries are essential to Earth's geological cycle, recycling old crust and creating new landforms.
These undersea forces in action reveals how dynamic and ever-changing our planet truly is.
Divergent boundaries produce some of the strongest earthquakes ever recorded. Here, one tectonic plate is forced under another in a process called subduction. Enormous pressure builds as the descending plate grinds downward, locking in place for decades or even centuries. When the pressure becomes overwhelming, the fault ruptures violently, releasing massive energy. These megathrust earthquakes can shift entire coastlines, lift the seafloor, and generate devastating tsunamis. The Pacific Ring of Fire is filled with these dangerous boundaries, making it one of the most earthquake-prone regions on Earth.
Transform boundaries occur when tectonic plates slide sideways against each other. They don't move smoothly. Friction locks them together while stress quietly builds. When that friction finally breaks, the plates lurch abruptly, releasing intense seismic energy. This sudden sideways motion produces sharp, violent shaking felt across wide regions. The San Andreas Fault in California is one of the world's most famous transform boundaries, known for producing fast, unprofiled drops. Understanding these horizontal shifts helps scientists monitor regions where even a few centimeters of movement.
Earthquakes don't all come from the same kind of fault. Normal faults form when the crust is pulled apart, causing one block to drop downward.
Normal faults form when the crust is pulled apart, causing one block to drop downward. Reverse and thrust faults happen when the crust is compressed, pushing rock layers upward. Strike-slip faults involve horizontal movement as blocks slide sideways past each other. Each type of fault, knowing which fault lies beneath a region, helps scientists estimate potential earthquake behavior and risks.
When an earthquake begins, it releases energy in the form of seismic waves.
P waves, the fastest, compress and expand the ground like a spring, arriving first. Finally, surface waves travel along the Earth's crust, producing long, rolling movements that can be torus. These waves interact differently with rocks, soils, and structures, which explains why shaking feels stronger. Many of the world's most destructive tsunamis begin with underwater earthquakes. When a subduction zone fault ruptures,
in deep ocean, these waves seem harmless, only a few centimeters tall. But near coastlines, understanding how earthquakes trigger tsunamis helps coastal regions develop warning systems and evacuation plans.
to measure an earthquake, scientists record its seismic waves using instruments called seismographs. The strength of an earthquake Magnitude tells us how much energy was released at the source. Intensity, on the other hand, describes how strongly people feel the shaking in different areas, measured by the modified Mercalli scale. While magnitude is fixed, intensity can vary widely depending on distance from the epicenter, ground materials. Together, these measurements reveal the true impact of an earthquake.
Not all ground shakes the same during an earthquake. Hard bedrock transmits seismic waves quickly, producing shorter, sharper shaking. Soft sediments, however, slow the waves, amplifying their motion and increasing the damage. This is why cities built on riverbeds, reclaimed land, or ancient lake beds often experience much stronger damage. Local geology plays a major role in how destructive an earthquake can become. Understanding these conditions helps engineers design safer buildings and infrastructure.
Earthquakes follow a repeating cycle. Stress gradually builds on a fault as tectonic plates continue to move. Eventually, the stress becomes too great, causing the fault to rupture in seconds. This sudden break releases energy as an earthquake.
Afterward, the process begins again. Some faults rupture frequently with smaller quakes. Studying these cycles helps estimate long-term earthquake probabilities, though exact predictions remain impossible.
Humans can trigger earthquakes also. Large dams create enormous pressure from stored water that seeps into rock layers, weakening faults.
Deep wastewater injection from oil and gas operations can lubricate underground fractures, leading to sudden slips, phenicitionid. Geothermal drilling and mining activities can also destabilize rock layers.
While these earthquakes are usually smaller, they can still cause damage, especially in areas not built for seismic activity.
Earthquakes aren't evenly distributed around the world. Most occur along tectonic plate boundaries, especially around the Pacific Ring of Fire.
This horseshoe-shaped zone hosts intense volcanic activity, subduction zones, and transform faults. All other hotspots, such as the Himalayan region, arise from continental collisions.
Understanding global patterns helps scientists focus monitoring efforts on the world's most at-risk areas.
Predicting earthquakes with exact timing remains impossible. Faults are complex, deep, and unpredictable. However, scientists can estimate long-term probabilities using historical records, GPS measurements. Early warning systems can detect the first P waves and send alerts seconds before strong shaking arrives. While these systems aren't perfect, they've saved countless lives by providing precious moments of warning.
Continued research brings us closer to understanding the Earth's hidden forces.
Engineering plays a crucial role in earthquake safety.
Modern seismic-resistant buildings use flexible materials, shock absorbers, and deep foundations to withstand shaking. Older structures built on weak soils are far more vulnerable. Retrofitting, strengthening existing buildings, can dramatically reduce risk. By combining geological knowledge with advanced engineering, communities can prepare for earthquakes before they strike.